Hello calculus students, welcome to your quiz review for sections 3.1 and 3.2 over the definition of a derivative and differentiability. In this quiz review I will show 5 problems. A few of them have a couple different parts, A, B, C, and you should write those down and work on them. Then at the end of the video you can use the chapters feature to go ahead to the solutions and explanations that you need based on what you missed. So use this quiz review to your advantage. If you're really not understanding, say problem number 2, take a look back at what exact topics that's covering. Look back at that assignment that covers those that we've been working on this past month and take a look at that assignment that you had to do and check out the recommended book problems or join my office hours to ask a specific question. But use this review to kind of perform a self-assessment and see what you know versus what you don't know, and therefore what exactly you need to study. So let's get started. If you need to pause the video for the questions, it's just going to be a quiet couple of seconds for each of the 5 problems for you to write it down. So feel free to pause at those points, work it all out, and then check with the solutions and explanations. Here we go. Here are the solutions just at a quick glance. I will put up number 3 in just a moment, but go ahead and pause the screen for you just to check, and then if you need to, go ahead and if you missed any of them or want to see how I worked it out, you can go to that specific part of the video. Here is problem number 3. The derivative here that I wrote got cut off, but the derivative here, the derivative in parts B, C, and D is pink. And again, if you need an explanation, go ahead to that part of the video. For problem 1a, f prime is 5. You can pause and see the worked out solutions here. Here for number 1b, the solution is f prime of x equals negative 6x, and the work is shown below. The solution to number 1c is f prime of x equals 2x plus 8. And once again, we use our definition of derivative to find that. For problem number 2, we're asked to find the equation of a tangent line. Our solution ends up being 9x plus 10. We are given the function and actually the equation of its derivative, so we don't have to do we actually don't have to do any calculus here. It's all algebra. We just have calculus understanding, meaning that we understand that f prime gives us the slope at an exact point, or the instantaneous rate of change. So in order to find the equation of any line, we need a point and a slope, and then we can use point-slope form. So I found the slope first. You could do either one first by plugging in the x value of -1 into our f prime equation, and then I just had to be careful with PEMDAS and negatives, so 15 basically here. 15 times 1 minus 6 is 9, so our slope's 9. Then to find the point, we already have half of the coordinate point. We have the x value, and so to find the y value, we need to plug into f of x, our original function, to find its y value. And again, being careful with the, cubing a negative gives us a -1 here. So it's -5 plus a 6 gives us the y coordinate. Therefore, our coordinate point is -1, 1. So now we have a point and a slope, and we plug it into point-slope form. Be careful with point-slope form. Remember, it's y minus the y coordinate equals your slope times the quantity x minus the x coordinate. So that's why it looks like they're like opposites here. And then we distribute the 9 and add the 1, so we end up getting y equals 9x plus 10. I ended up checking this on Desmos because you can always do that, which is really cool. So I have our original function in red. It's a cubic function, and then I put its tangent line in blue, it's obviously a line, it's linear, and we can see that the tangent line does represent the the instantaneous rate of change when x is -1. It's like sometimes a little bit hard to see, but we can see it. The blue line, our tangent line, does hit the function when x is at the coordinate point, at the coordinate point -1, 1, right here. And it's so steep here, like the function is so steep that it does look like the line smushes against the cubic function at more than one point, but it technically only hits here, and it represents how the function is changing at exactly that point. So we can see that we did this correctly, and we found the correct tangent line of our cubic function at x equals -1. For problem number 3 that has us sketching the derivative of each function, I'm going to actually sketch it on top of the function and talk through it rather than have it already written all out, because I think this is probably the most difficult one. So part A, it's just a linear function, but it's not horizontal. So linear functions can be either oblique, which just means it's not horizontal, it's like diagonal, or horizontal. A vertical line is not considered a function because it doesn't pass the vertical line test. So basically any oblique line, any oblique linear function is going to have a non-zero derivative. It's just going to be a constant because derivative is the slope. So we want to see how is this line changing, what's its slope. Linear functions have a constant slope, and in this case the slope is 2. You can go from any point to another point. You're rising 2 and running 1, rising 2, running 1. So the slope of this line's 2. It's the line 2x minus 1. We can just see that there. So in order to draw the derivative is, I'll do it in dark blue, it's just the constant y equals 2. So it's a horizontal line, and this is f prime of x, and it's just 2, which is pretty cool. And I should probably call this f of x. And there we go. You don't have to come up with this, you just needed to sketch it. But the idea is that any linear function has a constant slope or derivative. Constant meaning literally it doesn't change, it's just a horizontal line. All right, part B is extremely similar. It's just 3 different linear functions to make a piecewise function. So we can see that it goes from x is -1 to when x is 4, and here the line is horizontal, therefore the slope of a horizontal line is 0. And I will do this derivative here in pink to have some fun. So our slope here is 0. So again, this will be f prime will be in pink, and our original function we'll just call f, that's the blue function. All right, so the derivative is 0 from when x is -1 to when x is 0. Now technically there is, need to go back to pink, there is a hole here because the function is not differentiable at this corner spot here. All right, then we need to take a look at what is the derivative here for this piece of our piecewise from when x is 0 to when x is 2. And this is just like part A. And the slope is -2 because we fall 2 and run to the right 1. So our slope is -2 here. And therefore, from when x is 0 to when x is 2, f prime is -2. It's constant there. And our function is not differentiable when x is 2, so I put an open hole. That's because our function's not even continuous here, and if we're not continuous, we're not differentiable. Then from when x is 2 to when x is 4, we also have a constant derivative or constant rate of change. It's another line, and in this case the slope is half because we rise 1 and run 2, and therefore from when x is 2 to when x is 4, half is like right in there-ish. And then you can have either open or closed on the endpoints. Different books talk about it in different ways. It's not going to be that specific on your quiz, so that's okay. But as long as you understand that linear functions have constant rates of change, you should be okay. Let's move on to part C and D, where we have a quadratic function making a parabola, and therefore its derivative will be linear but not horizontal. Part C and D are probably a little bit more difficult for you to sketch, and that's why I just asked you to sketch it. It doesn't have to be perfect, but we do know that they are linear, so they're going to form just a diagonal line, and it shouldn't be like wobbly or anything like that. Basically, what we have to understand is that when our function, like let's look at part C, when our function is decreasing, its slope is negative, so the derivative should be down here. Then here, when x is 2, our function's neither increasing nor decreasing, therefore the derivative is 0. And then from 2 on, our function is increasing, therefore the derivative is positive. So if we call the original function f, I will again do the derivative in pink, f prime. What I do know is that the derivative is 0 when x is 2 because it's not changing. Then the derivative is negative, and it's pretty steep negative here, right? If we were to draw the tangent line here, it's a pretty steep negative, and then it becomes less negative here until it eventually hits 0. Therefore, our function is increasing just like this. I don't have exact values here. I don't have the tangent line sketched. I am just sketching, approximating. Then, so our derivative here is negative. All the y values are negative down here because our function's decreasing here. Derivative is negative when the function's decreasing. Then the function increases over here to the right of 2. Therefore, we continue, but now above the x-axis, something just like that. And this, in theory, is a nice straight line. So our function goes from decreasing to neither increasing nor decreasing at its minimum value to increasing. Therefore, the derivative goes from negative, then 0, and then to positive. D is just the opposite here, and our original function goes from increasing to neither to decreasing. And so it's basically the exact same explanation. Our derivative, I'll do again in pink, f prime, and that is a horrible dot, so we'll do that once more. So our derivative is 0 here at the maximum value, and we'll call the blue one our original function f. All right, when our regular function's increasing, that means our derivative's positive. Therefore, it's somewhere up here. I don't want to run into the other picture. Then, when our function is decreasing, our derivative is negative, so it's down here. And so this is also an oblique line, meaning it's just not horizontal, and it just has a negative slope instead. So really, C and D are the same exact idea, but because of the upward-facing versus downward-facing parabola, our linear functions have either a positive or a negative slope. So we have to understand the relationship between a function and its derivative. Here are the solutions to problem number 4. The idea is explained in a lot of detail in number 3, but it's the relationship between a function and its derivative when a function is increasing. So in this case, our red cubic function's increasing between -4 and 1. That is when our derivative is positive for part A. When our function is decreasing from -infinity to -4 and from 1 to infinity, that's when our derivative is negative. And for what x values is f prime of x equal to 0? Well, when our function's neither increasing or decreasing, so a lot of times at minimum and maximum values, locally minimum and maximum values, right? This doesn't have any minimum or maximum value since it goes to the infinities, but at these local like dips and like high points here, called local mins and maxes, f prime equals 0 because it would have horizontal tangent lines here. So therefore at x equals -4 and x equals 1, f prime of x equals 0. And the other thing that a lot of you ended up fixing, what we initially struggled with, was writing intervals, and we have to write intervals using the x values going from left to right. For problem number 5, I definitely recycled this piecewise linear function we had from problem 3. So in this case, we have this function g of x. We want to know when it's not differentiable. Remember that functions are not differentiable when we have cusps, corners, vertical tangents, which we haven't really seen yet, but we will eventually, or when it's not continuous, aka discontinuous. I asked you to use the domain from open -1 to 4, meaning disregard at x is exactly -1, at x is exactly 4. I wanted you to focus in between those, which is why I wrote that here. So we're not differentiable at this corner when x is 0, and we're also not differentiable at this jump discontinuity at x is 2. For part B, we are discontinuous, aka not continuous, at this jump discontinuity x is 2. And part C, we are continuous when x is 0, but we're not differentiable there. So if you are continuous, you may or may not be differentiable, but if you're differentiable, you're definitely continuous. So kind of an interesting concept here. At x equals 0 at this corner, we are continuous because we do not lift up our pointer, but we're not differentiable. And at x is 2, we're neither because we're discontinuous. I really hope that this video helped you out to kind of self-assess and see exactly what you need to study and what you don't. And best of luck on your quiz.